Welcome to Brain Vision.
In this problem, we have another reheat Rankine cycle. Again, ideal. We have a little different condition here. This time, we coming out of the high pressure turbine, we have saturated vapor, and then that's reheated. And then we're basically in the two-phase region here, coming out of the low pressure turbine. So again, I should probably, like I said before, make this a black line. So we have, all these entropies are the same, because we have ideal cases for the turbines and for the pump. The high pressure, so we're in English units now. The high pressure side is at 800 psia. Again, we have a quality factor of 1 at 4. Let's see here. We also have, let's see, heat is transferred. We have, so we have steam is cooled in the condenser by cooling water from a nearby river. So the river temperature is, what do you call it? Is 45 degrees Fahrenheit. So that enters the condenser here, and so we basically have a heat exchanger here to condense this vapor. Up here we have 900 degrees Fahrenheit, and down here we have 1 psia. So very low pressure down here in the condenser. Let's see here now. T1, again, we are at saturated liquid here. So T1 is roughly 101.7 degrees Fahrenheit, because we're at a very low pressure here. Let's see here. Yeah. Anyway, yeah, that's kind of a, oh yeah, no, yeah. I'm thinking Celsius. Like, why is that over 100 Celsius? No, it's Fahrenheit. So that's why it's below 212. So 212 Fahrenheit is where water boils. So yeah, why we're way below is because we're at very low pressure. Now we can figure out the enthalpy there, and that is 69.72 BTU per pound mass, and we can figure out the specific volume, which then allows us to figure out the work that is being done, put into the pump with a specific work, which then allows us to find the enthalpy at 2, as always. Then we can look at point 3 here. We have the pressure and the temperature, so we can get the enthalpy and the entropy. Entropy at 4 is the same as entropy at 3, so we can figure out the pressure at 4, which is actually pretty low. We drop down a lot in pressure. And then we can also get the enthalpy at 4. We can find the enthalpy at 5 because we have let's see here, the temperature at 5, and we know the pressure at 5, because this is also, I should just write that in here, P5 equals P4. So we know the pressure and temperature at 5, so we can get the enthalpy and the entropy. Entropy at 6 is the same as the entropy at 5, so we have two properties there, pressure and entropy. So we can get the quality factor, and we can get the enthalpy at 6. So now we have the enthalpy at all of our states, inlets and outlets. So we can figure out the heat transfer in, which is H3 minus H2 plus H5 minus H4. So that's the specific heat in. Out is just H6 minus H1. So that is the specific heat transfer out of the in the condenser. Now we have let's see here. We can get the thermal efficiency knowing that that's just 1 over Q in, Q out, 1 over Q out, all over Q in. So we can get that is 39.4%. So then we're asked about the, let's see, the net power output and thermal efficiency and the minimum mass flow of the cooling water required. So again, remember we have cooling water flowing here through the, and condensing this, this liquid here, or this water here. And so we know we need that the let's see here, the rate, this value here, Q dot out, the heat transfer out of the water, which would be the heat transfer, sorry, out of the water in the cycle, will be the heat transfer in to the water from the river. So that's just Q dot in minus W dot net. Just looking at a control volume of this whole system. We can W dot net. We could figure that out if we wanted to, but we can also just say that that is the thermal efficiency times Q dot in. So then this winds up being, these two terms wind up being 1 minus thermal efficiency times Q dot in. And we know this and we know this. Or we can figure this out because we have the specific heat, specific heat in. Let me see here. Why do we have, let's see here. I'm trying to figure out, oh, we were told this. I must not have written that down here. I should have written that down here somewhere. We were told that Q dot in, put it here, equals 6 times 10 to the 4th BTU per second. All right, so we were told that. I was wondering how we got that. Although we should be able to get, well, we don't know the mass flow rate, in the cycle here. I was going to say we should be able to get that from here, but we don't know what m dot is. So we could then get m dot now that we know that this specific Q in and the power in. So we can figure out when the heat rate of heat transfer out is 3.6 times 10 to the 4th BTU per second, which means that that is the heat transfer that needs to go into the water, into the river water, which we're assuming is just is just water, saturated liquid. So we can get the heat capacity of that, at constant pressure, which is 1 BTU per pound mass Rankine. And then we get the temperature difference. We have the temperature at the inlet, and for the minimum case, we would need the temperature at the outlet would be the temperature here at 1, so that the outlet temperature of the river water and the process water have the same temperature. So that would give us the minimum, which we would obviously probably need more than that. So the minimum mass flow rate, we'd have that change in temperature. So again, we can plug all that stuff in and we get a mass flow rate of 641 pound mass per second of river water that we need to flow here that would be the minimum to get this, if we had a perfect heat exchanger, to get the temperature down here, to get, to do the condensation that we want.